I'm Musa Mabandla. I'm the professor of physiology, specializing in neurophysiology. My research interests are focused on neurodegenerative disorders, particularly in the brain. The diseases that I'm looking at are Parkinson's disease, Alzheimer's disease. We've now moved on to schizophrenia, as well as the effect of drug treatment on the brain for HIV. But basically, in all of our projects, we try to look for non-conventional ways of treating the diseases. The reason for that is the cost of the treatment, and the fact that we live in a country where very few of our people have access to adequate medical aid and therefore treatment. 80% of the people in the country depend on government support. So in essence, in assisting with the treatment profiles, we've tried to look at non-conventional methods of treatment. So for example, for Parkinson's disease, one of the things that we looked at was the use of exercise. And the reason for that is when you have symptoms of Parkinson's disease, you tend to limit the use of the impacted limbs. And so by actually forcing or trying to use those limbs, you are actually slowing down the disease projection. Now, the important thing again about Parkinson's disease is that as it stands now, it cannot be cured. Once it starts, it will progress until leading to death. So in essence, what we're trying to do, whether it's through pharmacotherapy or through these non-conventional means, we're trying to slow down disease progression. Hopefully in the future, there will be a way of treating and actually stopping disease progression. And in line with that, we have now moved a little bit into nanotechnology, where we actually do insert nanoparticles into the brain and see if there is a way of actually, like we do with animal models, of actually impacting directly where the disease impacts the brain, so that again there we can stop the progression. We're also looking at Alzheimer's disease, and for Alzheimer's disease, again, we're trying to find ways where we slow down progression, find ways where we can see if there are biomarkers. By biomarkers, I mean things that we can see early on that will assist in the diagnosis of the disease. And once we do find those biomarkers, find ways of actually treating or getting rid of whatever is causing the release of those chemicals, so that in essence we will be again slowing down the progression of the disease. So in terms of schizophrenia, what we are trying to do is we are again developing models. Now when I'm talking about models, I'm talking about animal models. The reason for us looking at developing models is again the cost of actually buying ready-made or produced or manufactured models, as those have to come from overseas. And in our resource depleted environment, we do need to find ways of actually attenuating the use of funds. So we are developing these models, and we have successfully developed models that we can use in terms of looking at the different modes that lead to schizophrenia. In those projects, we are linking with clinicians, where from a basic sciences perspective, we are working with animals. So once we've developed those models and then we use treatment for those models, we now translate that research by collaborating with clinicians, who then come up with modes of treatment and basically have a way of where we can meet or translate the research into something that is usable by the community. Now, the last sort of, the last cohort of experiments that we are working on have to do with HIV. Initially, we looked at drug toxicity, where the constant use of HIV drugs may lead to toxicity. We produced a number of PhDs in that, but now we've moved on to looking at how drugs that are injected systemically or are consumed systemically get into the brain. Because you must remember that HIV does cross the blood-brain barrier and goes into the brain. Now, as a neurophysiologist, we are focused on impact on the brain. So what we're trying to do now is to look at how we can ensure that drugs do cross through the blood-brain barrier, because the blood-brain barrier, as the words suggest, blocks entry from the system into the brain. And by working with various types of drugs, we are trying to find a sweet spot where we can actually get the drugs to cross the blood-brain barrier and actually have an effect on where the HIV reservoirs are. We have been successful in our animal models in doing that. We are now continuing with a new cohort where we're looking at different types of drug combinations, and hopefully there we can assist in looking at the impact of HIV or decreasing the impact of HIV in the CNS or the central nervous system.